Welcome to a phenomenal edition of Rebellion's educational series. I have a super brilliant guest with us today. Dr. Mark Sepanski went to MIT, wrote an amazing book on compact Lie groups. And Doctor, why don't you tell us about, first of all, what a Lie group is?
Huh. Well, thanks for having me here. It's really a pleasure.
The honor's all ours.
Yeah. I guess the place to start really is symmetry. So symmetry is sort of often why the universe is the way it is. And the easiest maybe picture you can have in your head of symmetry would be a circle. So if you start with a circle, you can rotate it back and forth on itself all at once, and it'll still be the same. And that's what I mean by symmetry. But it actually has some other properties. It's very contained, meaning it doesn't go off to infinity. This is sort of a notion of compactness. And it actually has a type of arithmetic to it. You can multiply elements of the circle because they sit in the complex plane. So it has algebra, it has geometry, and it's in this very compact space, and so it's called a compact Lie.
So Emmy Noether's theorem says that if it contains symmetry, then it implies conservation law. So do you want to jump on that and explain to our viewers what that means?
Right. So the way it works is you'll have a system that's usually described by some types of functions, and you'll have a group, a type of symmetry that's kind of moving these functions around in a certain way. And whenever these symmetries are acting, it is often the case that they will end up showing you what is preserved in this system that you're studying. So it's often like in physics, you'll hear things like energy is preserved, or in some cases, momentum might be conserved. And those are coming out of these symmetries that are acting on the systems there.
Energy management and energy exploration, would you say maybe, and maybe on well depletion ratios?
Well, so in all those systems, you also have sort of corrosive entropy going on and frictional type forces that
Yes, you do.
make it more complicated. But yeah, I mean, in essence, we only have a finite number of resources, and it might be that we're burning through them. But back to your original question on the Lie groups, they really are this sort of miracles of mathematics that sit in the intersection of the big areas of math. One is called algebra, which studies like generalizations of number systems. And the other is analysis, which would study calculus type related generalizations. And when you have something that can be studied sort of equally by both lenses, you tend to be in the category of Lie theory. So in some ways, they're the case where all the miracles go right. Instead of what can go wrong goes wrong, what can go right goes right when you tend to work in representation theory or Lie theory. So
would you like to tell us about some of your current research?
Well, that's a great question. So here's what's happened. You have some embodiment of a symmetry, and it manifests itself in nature by what's called a representation. That's sort of how it reaches into the world and sort of shifts things about, okay? Often these things are infinite dimensional spaces, which make them a little more tricky to deal with. But mathematicians have been studying this for a long time. Now, what math people like to do is they would like to say, well, can we make a list of all the ways these types of representations can occur? Do we know all of them? And of course, even that's a little bit of a lie. You first have to do some work that kind of says for any type of symmetry, you can break it into like indivisible pieces. So then the question is, can you say what all these indivisible pieces are? And as is weirdly but commonly the case in math, the answer is often yes, but even though I can give you what the list looks like, I can't write any of them down initially. So sometimes you can classify things without writing them down, which is a little weird. Sort of just like there exists a list of 100 things. I can't tell you what any of them are, but I know there are 100, okay? So this was done quite a while ago. And then the question is, well, if you can classify them, can you actually also write them down? And then can you study more of their structure? Because people who are going to be using them want to know more than just, oh, it's there. They would like to know what it looks like, what special properties it has, and that. And so on recent work, we were looking at some of these representations and writing down both what they look like and also how they behave in this special way. And here's the special way. I mean, it sounds a little weird at first, but if you live on the plane, you've got like your X variable along the X axis and the Y variable, and they're just very different. X and Y are completely independent variables, okay? But if you were to restrict your attention to the circle again, there X squared and Y squared is 1, so they're not independent anymore. X and Y on that sort of space become dependent. And so what you would like to do is write down all the dependencies. And then it turns out all the dependencies, they have dependencies. So the dependencies have dependencies. And then the dependencies of the dependencies have dependencies. And they form, like, it turns out, in this case, a finite chain of dependencies that kind of spreads out the behavior of a representation in a really convenient way. This is called a resolution in math. And if you have these resolutions, it allows you to kind of pull out special information about them. So we wrote down a bunch of resolutions for a category of these representations.
Wow, that's very, very cool.
It is. It's actually, you know, a lot of times math, I mean, you know, math can be complicated sometimes and technical, but it was kind of pleasant in the end because there were all these awesome pictures that were attached to it.
What challenges do you think we'll be able to solve with this?
Well, so to be honest, we were just doing this for other mathematicians, but it turns out Lie theory is kind of a hugely impact field in a lot of areas. So for instance, physics is a big user of Lie theory. If you look at, I guess it's called—
I assume particle physics or theoretical physics?
Yeah, theoretical and some experimental. I mean, like, if you want to know, if you run those chemicals through the spectroscopy.
So really, the future of particle physics is going to be in space then, huh? We're kind of limited until we can do some more space exploration. I mean, how much can we really understand about string theory until we get out there?
Well, you know, it's interesting. There are people who call string theory not even a theory. And what they mean by that is that we just can't test sort of anything. So
no, it's very tough. My buddy, Professor Brian Keating of the UCSD, spent 10 years studying what he thought was proof that string theory existed from the cosmic beginnings, but it turned out just to be cosmic dust, actually. And so he spent 10 years of his life working on dust, but he got nominated for a Nobel Prize, but then when it turned out to be dust, you know, he lost. But
well,
so actually, he wrote a book on it called Losing the Nobel Prize, but yeah, anyway.
Yeah, that would be fun. String theory is pretty cool. It's mostly just kind of theoretical math and hard stuff. It touches on representation theory, but things like the standard model for why the universe is the way it is, all the particles, how they all fit together, that's all expressed just as a bunch of Lie groups and their representations. There are, well, you know, things like this. So a lot of things come down in a lot of applications of mathematics. You want to solve some PDEs, some partial differential equations. You can't solve those sort of like just write down the answer. but you have to model them with a computer. And the model needs to be fast and accurate, and it's very hard. And all of that really gets translated into a subfield of math called linear algebra. It's the same with, a lot of all the machine learning. It turns into these huge linear algebra problems that you have to be able to solve quickly and fast. And it turns out on a lot of problems, the way you try to solve it makes a big difference. And there are techniques from Lie theory that come into this. So you might try to solve your equations and preserve certain quantities. And if you're doing that, then you're almost certainly touching on Lie theory. So anyway, it comes up in relativity, in, of course, spin particles. Why do things have spin? That's always a statement about a Lie group. So for instance, here's a famous compact Lie group. It's called the orthogonal group. They're these linear transformations of space that preserve length, okay? And it turns out, as I said, it's a Lie group, so it's not only an algebraic thing, like you can multiply them together, but it actually has a geometry to it. It's something you can do calculus on. It's some weird curvy surface of high dimension. And it turns out it has half of a hole in it. So what I mean by that is, suppose you're in some space and you want to know if there's a hole in the space, but you can't really see the hole living in it.
No, totally, yeah.
You could take a peg, pound it in, and then wander around with a string for a while, and then eventually go back to the peg. And if you can pull the string all the way back to you, there's no hole, okay? But it turns out in these orthogonal group, if you do this with the string, you wrap it around once, it gets stuck. So there's a hole in your space. But the weird thing is it's a half of a hole, because if you wrap the string around that hole twice, it pulls free. So it's really bizarre. It's got like a half of a hole in it. You can see that actually, I don't know if you've seen people do tricks with coffee cups. If you hold a coffee cup in your hand and rotate it once, it turns out it's not quite, it's come back to itself, but you can tell by your arm being cocked in a strange angle, things aren't right. But if you rotate it one more time, then your hand returns this is actually, there's a way to describe that as this path in this orthogonal group. But anyway, so it has half of a hole.
That was a great way you explained it. Was fantastic, Professor. By the way, I apologize. I didn't even mention, you're also a professor. You teach my buddy, do you know Professor Poucher?
Yeah, he's a great guy.
He's a great guy. Isn't he a great guy? I love him.
He is so kind and encouraging. He's just sort of a wonderful human.
Yes, yeah. A wonderful human would be my thoughts exactly.
Yeah.
So, I really enjoyed.
And we used to, anyway, he runs this big computer contest. And
I was introduced to him by one of my best friends, Dmitry Korolev, who said, or Dima as I call him, Dima was like, you got to meet this professor. He's fantastic. And actually I came across some of your work and I was like, whoa, this Dr. Sepanski guy is super smart. I've got to get him on my show and learn whatever I can from him.
Well,
that's the way I am with this show. I'm like a scientific beggar on the street, just trying to get morsels of information from brains like you.
Oh, it's fun. I love learning things and talking to people about what they study. It's delightful.
I mean, I have a very narrow space where I just apply Bayesian networks to the economy to try and make 90-day and 30-day predictions on various assets.
Yeah, your job sounds really cool.
No, but it's much more mundane compared to your job. Your job is far more interesting and exploratory, and that's why Rebellion has, shifted. We are, a binary firm. We are both an asset management and a think tank. So, much of our focus is purely on learning, getting published in both Journal of Financial Data Science, with the Air Force. We're doing research partnerships now with 6 schools. So it's really just a research and education focused firm that also happens to run money quite fairly well. Our AI Global was up like 23% last year. So,
oh my goodness.
Yeah, no, we had and it was actually, it does a great job. So my partner, Dr. Spencer Greenberg, started under Jan LeCun, which was, Spencer's the best. If anyone wants to check out his rationality talks, Spencer's a deep thinker. I'm just a grinder. I'm one of those, I don't have deep thoughts like that.
Everyone has different talents. Some are worth more.
Well, so I guess, these are pretty quick shows. I apologize for that. But now that we're concluding, what would be your parting thoughts? What would you like to express to the audience? Please take your time.
Well, I would say this, especially this is to younger people. Mathematics is a vehicle to a lot of really good jobs. You don't have to be a math major.
Very well said.
Yes. If you can't do a lot of mathematics, you're very limited. And the jobs you can get having a little bit of math are interesting, fun, they can be well paid. So what I wanted to say is this, that really people tend to think that only geniuses can do math, and that's just not true. Everyone can do math. It's just a matter of effort. If you really keep trying and keep at it.
100%. I couldn't agree more. Math is without a doubt the greatest grinders avenue for education that there is. French is something where I feel like you can or cannot do it. But with math, if you work hard, you can do it. By the way, my coffee mug is Star Wars. I love your shirt.
Thank you.
Rebellion is very Star Wars obsessed, as I am their CEO, and I'm highly Star Wars obsessed. So, I had to point that out. I know, Professor, you mentioned, earlier in the, before we started, that you're not a fan of episode 1, which I am not a fan of either. My favorite, of course, is Empire Strikes Back. What can I say?
Yes, that's the answer.
It is the end. I can't help it. I can't help it. And we're both very upset about the evil curve, the evil slope of Anakin. Was just absolutely ridiculous. Crazy. No. In episode 3, Anakin goes from Anakin to this nearly satanic creature way too quickly. I mean, this is like. He goes from nice guy to blows by Gordon Gekko in 30 minutes. So
yeah,
he's not happy with that either.
Who they had writing those scripts, and also why didn't they come up with new scripts?
Yeah, the Rogue One was surprisingly fantastic. I was blown away by Rogue One, and actually, when I was at Last Jedi, I was very upset. I went with one of my best friends, Han Kui, who's a student of mine at Columbia Math a decade ago, and he actually he liked Last Jedi, but I was very upset with it. So,
well, there's a lot of nostalgia. I mean, I like them. It's just, I like them mostly because of the nostalgia.
Yeah. I mean, we are an educational show, but I think Star Wars is at this point such a significant part of our culture that, the education of it, I hope you don't mind that we did discuss Star Wars on the show.
Oh, sure. I'm happy to.
Happy to edit it out afterwards if you don't like it, Professor.
No. It'll probably be the most interesting part of the show.
Oh, no, not at all. No, this was a fantastic show. It's, no, this was a lot of fun. And, thank you so much for coming on. And, I hope to have you on another time. Maybe we'll get you, Professor Poucher, and the three of us can have a chat one day. That'll be a lot of fun.
It would be fun because, he was a mathematician in his youth. I mean, he was a mathematics.
He was everything. Oh, no. He was the guy's Renaissance man. So, just, super, super impressive. And my last comment is I did not like the Wookiees from Return of the Jedi. Did you like the Wookiees? I think you might have liked the Wookiees. Be honest if you did.
You like the Wookiees just because they're a cool creature, but it's weird. I mean, are they really technologically savvy or not?
I just thought they were a little campy in the way that they were delivered as, kind of characters. I just, a little bit like the Joker from the original Batman series with the shark on his foot. They were a little bit silly almost. And maybe it was playful and they wanted it in that kind of R2-D2 playful way, but maybe I just felt they went too far with it.
Yeah.
Not,
See that. Yeah.
Yeah, nevertheless, it was still fantastic. And I also want to mention that in Rogue One, the battle scene with Vader is unbelievable. So.
Oh yes.
My mug is a Vader mug.
That last battle scene, that was just mind blowing. It was like,
wow. Yeah, it was Yeah, it might be my one of my favorite moments. Who knows? But anyway, this was fantastic, and I'm so happy we got to talk today, Doctor.
It was
And
fun.
you stay safe during these crazy times, okay?
You too. Thank you for having me.
Oh, pleasure is
Bye.
all mine.